1 equals 1. 1 plus 3 is 4. 1 plus 3 plus 5 is 9. 1 plus 3 plus 5 plus 7 is 16. Let's look at a few more terms. Do you see a pattern? 1, 4, 9, 16, 25, 36, 49, and so on. All of these are perfect squares. Namely, 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. Magical, isn't it? Let's look visually at it. Start with a normal square with side 1 unit long. Now, we want to keep it a square, so we need to add 3 more squares to the side. This gives us a square with area 4. Now, to keep this square a square by adding more squares, you need to cover the side and the corner, giving area equals 9. Finally, to keep this square a square by adding squares, we need to add 7 more squares to get a square with area 16 squared units. You can try this out for larger and larger squares and it will work out. Why? Let's see it with some rigor. Take a list of the first few natural numbers and duplicate the odd numbers. What you will observe is that the difference of any two consecutive odd numbers is always 2. You add 2 to an odd number to get the next odd number. Let's pick out an odd number, say 5. 5 is 2 plus 3, but 3 is further 2 plus 1. So 5 is 2 plus 2 plus 1, which is 2 times 2 plus 1. This gives us another nice pattern. All odd numbers can be written in the form of 2n plus 1, where n is any natural number including 0. Now, you can see that this is also the general term of an arithmetic progression. Just compare the two. The first term is a, and 2 is the difference, with the only difference being the starting point of 0 versus 1 for n. So, we can check the sum of odd numbers by plugging them in the general sum formula for arithmetic progressions. It is given by half of the nth term multiplied by 2 times the first term added to the difference between the terms times n minus 1. Here's a quick and elegant derivation demonstrated below. Now that we know the validity of this formula, let's just plug a equals 1 and d equals 2 in it. We get the sum as n minus 2 times 2 plus 2n minus 2. 2 minus 2 is 0 and 0 plus 2n is just 2n. The 2 in the numerator and denominator cancel out, leaving us with n squared. Exactly what we expected. This also means that the difference of any two consecutive perfect squares should be an odd number. Let's quickly check it out. N plus 1 whole squared minus n squared. N plus 1 whole squared is a binomial which can be expanded as n squared plus 2n plus 1. Subtracting n squared from that, we are left with 2n plus 1. Same as we expected. Now that we have the truth established for natural numbers, what about all real numbers? No one is stopping us from plugging n equal to say pi. So here's the graph of y equals 2x plus 1. We have replaced n with x to depict real values. The yellow dots depict the odd numbers. Area of the graph should ideally be x squared, and it is for the intervals between two natural numbers. However, what about all the real numbers? Rate of change of x squared or its derivative is 2x, not 2x plus 1. Integral of 2x plus 1 is x squared plus x, not just x squared. Explaining this discrepancy is left as an exercise to the intelligent viewer. Enjoy the dancing equations.